Let's look at this relationship of boiling point and atmospheric pressure. The atmosphere does exert pressure. If you're uncertain of that, watch this and you'll really see.
A small amount of liquid water is placed in a can and boiled. The can fills with water vapor. Quickly inverting the can into ice water causes that vapor to condense, and atmospheric pressure crushes the can.
We find that the boiling points of liquids are influenced by atmospheric pressure. Higher atmospheric pressures, which actually happen lower, close to sea level, result in higher boiling points. Lower atmospheric pressures, which are from high up in the mountains, result in lower boiling points. What's going on? Remember, when a liquid boils, the molecules have enough energy to escape into the gas phase and to break IMFs. But if the atmosphere is pushing a lot on the developing vapor, it's going to take additional energy to escape into the gas phase. And the closer to sea level, the more atmospheric pressure. Higher atmospheric pressure makes escape more difficult and results in higher boiling points. Lower atmospheric pressure allows escape more easily and results in lower boiling points. So check this out. This is one of the strangest videos that you'll see. We're going to watch water boil when it's cold. What? So watch. If you ice a container of water, in other words, cool it from the bottom, it doesn't start boiling. But if the container is sealed and then the vapor above the liquid is cooled, the water will boil even though its temperature is below 100 degrees. So now think about it for a minute. By cooling the vapor, you're condensing some of it and creating a lower pressure above that liquid. Lower pressure above leads to lower boiling points. Watch.
Water boils in a flask, and later the flask is stoppered and removed from the hot plate. When ice water is poured over the flask, the water begins to boil. When the flask is cooled, the pressure of the water vapor decreases, which decreases the boiling point of the water. Note also that the temperature of the water in the flask decreases in the process. Ice water may be poured over the flask several times as the water cools. Boiling occurs each time ice water is poured over the flask.
Vacuum distillation is a technique that relies on using a vacuum system to decrease the pressure above a liquid so that it will boil at a much lower temperature than its normal boiling point. This is very necessary for large molecules which have high boiling points. Pressure cookers do the opposite. They rely on trapping vapor above the liquid, and that increases the effective pressure above the liquid so that it will actually boil at a hotter temperature than its normal boiling point. Think about that for a minute. A hotter cooking temperature results in faster cooking. Pressure cookers are used to cook things more quickly. So why does atmospheric pressure matter? Remember, boiling has several aspects. The molecules have to move faster, the IMFs have to break, and the molecules have to disperse into the surrounding atmosphere. A higher atmospheric pressure interferes with vapor bubble formation and gas dispersion, so a higher temperature is required to overcome this. Atmospheric pressure in general increases as sea level is approached, and it tends to be lower in the cold months than in the warm months. So what's a normal boiling point? Water boils at 100 degrees centigrade when the atmospheric pressure is defined as normal pressure, 1 atmosphere or 760 millimeters of mercury. That's called the normal boiling point. But water boiling in the mountains would always be what? Warmer or cooler than 100 degrees centigrade? And water boiling under 2 atmospheres of pressure would always be what? warmer or cooler than 100 degrees centigrade. So what about evaporating, and how is it different than boiling? Evaporating can happen at any temperature. Evaporating describes molecules escaping the surface of a liquid to enter the gas phase. This is a surface event. Higher temperatures do lead to more evaporation. This forms more vapor above the liquid. Heavier molecules are going to be moving more slowly at the same temperature than lighter molecules, so evaporation is more difficult for heavier substances. And stronger IMFs make it more difficult for molecules to escape from the liquid surface, so evaporation is more difficult in substances with strong intermolecular forces. Evaporation happens from the surface. Note that only molecules from the surface are managing to escape. And molecules can begin to escape but get attracted back into the liquid surface. This is why we end up with an equilibrium between the vapor above in a closed container and the amount of liquid that still remains liquid. A somewhat more sophisticated way to talk about boiling points and evaporation and IMFs is to talk about the vapor pressure of a liquid. So what do we know already? We know that all liquids evaporate to some degree at every temperature. At a higher temperature, more of the liquid will form vapor. In an open container, we would simply see the vapor disappear as it disperses off into the surrounding atmosphere. But what if we put a lid on the container? Now the vapor is trapped. Molecules in the vapor phase will actually collide with the liquid phase, and some will be pulled back in. There will be a point where we have an equilibrium set up. And for that liquid at that temperature, there's a maximum amount of vapor that forms and remains in equilibrium with the liquid. This is what we define as the vapor pressure of that liquid. So in this closed container, we can actually measure the accumulation of trapped vapor. And the amount of trapped vapor, and thus its pressure, is going to depend on the specific liquid and the temperature. This actually can lead us to another definition of boiling point. A second definition we have for boiling is that a liquid boils when its vapor pressure matches atmospheric pressure. So let's compare two different liquids. The red liquid has a higher vapor pressure. Note the larger amount of vapor, and thus a higher pressure, above that liquid. This suggests that this is a low mass substance, or it has very weak IMFs. This red liquid is going to have a low boiling point. That's because it's already well on the way to its vapor pressure matching atmospheric pressure at this temperature. If we look at the purple liquid, it has a lower vapor pressure. This suggests high mass molecules or strong IMFs, or maybe both. Note that there's very little vapor, so there's a low vapor pressure. This is going to lead to a high boiling point. This must become much hotter before its vapor pressure can match atmospheric pressure. Remember that all these events on this slide are not the same. Decomposing water is a chemical reaction where the covalent bond inside water molecules is broken and the free elements hydrogen and oxygen are formed. Evaporating water is any temperature event happening from the surface of a liquid, in this case water, and the only thing that's broken is IMFs between the liquid molecules, as a few of them become vapor phase molecules. Boiling water is a true phase change. The entire substance reaches a temperature at which it is ready to become a gas, and the last amount of energy goes into breaking all the IMFs. This moves one molecule of water separate from another molecule of water and separate from another and another, so that we have a large number of independently moving water molecules that we now call steam. Try to apply all these concepts about IMFs and properties by working through the required worksheet. This counts as a quiz on this module, and you can enter your responses online. Read carefully and think hard about the concepts because this should solidify what you've been thinking about in terms of IMFs and phase changes.